Hello and welcome to lecture 42 of analog integrated circuit design. We were in the middle of discussion on common mode feedback circuits. The common mode feedback circuits can be very simple, in which case probably not much more is to be done. The components in the op amp stabilize the common mode feedback loop as well. Sometimes when the common mode feedback circuitry is complicated, you have to take some special steps to stabilize it. In either case, the common mode equivalent circuit, the common mode half circuit looks like yet another feedback loop, which could look like either one or two stage op amp. Okay, we have seen examples of both. Now in this lecture, what we will do is look at some other kinds of common mode detectors and see how to use them in feedback. So first a quick review of a very simple this is a fully differential single stage op amp. I mean this part is the transconductor, and when loaded by capacitors, it becomes an op amp. These are the two resistors are the common mode feedback detector. Now the differential equivalent circuit is very simple. Okay. So the differential equivalent circuit, differential half circuit has a DC gain, that is from Vd by 2 to Vom of minus Gm1 by Gds1 plus Gds3 plus Gcm. Okay. Now when you have the full circuit, at this voltage you will get minus of Vom with a fully differential excitation, and the gain remains the same, that is the gain VOP minus Vom divided by Vd will be equal to Gm1 by Gds1 plus Gds3 plus Gcm. Okay. And the unity gain frequency will be Gm1 by C. Okay. The C includes the load capacitance that you have plus any parasitic capacitance occurring at this node. Okay. Now in fact this transfer function is simpler than what we had for the single stage single ended op amp. If you recall, in the single stage single ended op amp, we took the current of M1, mirrored it, and the output was taken from this side. Now because the current mirror has some pole in its frequency response, half of the current was going through some pole and the other half was coming directly. So we had this mirror pole and 0. In the fully differential single stage op amp, we do not have any such thing. Okay. So that is actually an advantage of the fully differential single stage op amp, and the other things remain the same. Okay. So the noise we have already calculated, the input referred noise turns out to be exactly the same as what we had in the single ended op amp. I am not going to work it out here, but we have already looked at how to calculate the noise of the fully differential circuit from the differential half circuit. You just have to calculate the input referred spectral density or the output voltage noise spectral density and then double it to get the corresponding quantity in the fully differential circuit. Now, in this case we also have RCM which creates noise, but I have neglected the noise from RCM. Okay. And the slew rate will be I naught by C, because all of I naught flows into M1 or M2, and the rate of change of the output voltage will be related to I naught and this capacitor C. Okay. And finally, the offset again will be similar to what we had in the single ended single stage op amp. It will be equal to sigma Vt1 square, with this is the mismatch between the transistors M1 and M2 plus the mismatch between the transistors that form the load times GM3 by GM1 squared. Okay. Again I have neglected the contributions from R. The mismatch in RCM will contribute to the overall offset, but because the value of RCM is so large, that can be neglected. Okay. And the common mode half circuit of this, which we also discussed earlier, there will be a parasitic here. Okay. Now, in this loop the integrator is formed by the GM of M3 and 4 and this capacitor 2C. So, the unity gain frequency of the common mode feedback loop is GM3 by C, and there is a parasitic pole due to this R and that C. Okay, and this C is nothing but 2 times CGS 3. Okay. So, this is and the left half plane of course at minus, sorry, this is RCM by 2, RCM times CGS 3. Okay. And we would like this to be at a frequency much more than the unity loop gain frequency. Otherwise, what happens is when you have a common mode excitation, the output will ring. Okay. Now, there is a way to fix this, and that is to have a capacitor CCM across RCM. That is, if the pole happens to be at a low enough frequency, then you will have ringing, you will have poor phase margin in the common mode feedback loop. The way to fix it is to have this capacitor which adds a 0 or a negative delay. So, in that case you can again calculate the poles and zeros. Okay. Now, the pole and zero calculation in this case is a little complicated, but what I will assume is that the impedance of RCM by 2 and the impedance of the CCM are much more than the impedance of the load capacitor, because what happens is when you have these coupled RCs, you have this C and then R and then C, you will have some poles which cannot be calculated so simply. Okay. Even this is an approximation. When this part of the circuit has a very high impedance, insignificant current is drawn from this, and we can act as though this circuit is isolated from that part. Okay. Now, if this is not the case, then you have to go and calculate it exactly. Okay. So, in this case you can calculate the pole and 0. and the 0 is at okay, and from all of this you can calculate the phase margin in the loop gain function and make sure that it is sufficient. Okay. There are many ways to calculate the stability of this. Okay. We have seen circuits like this in other occasions, like when you calculate the frequency response of a common source amplifier, we have a similar circuit with a capacitance from the drain to ground, capacitance from the gate to ground, and a capacitance between gate and drain. Okay. And we know where the poles are in such a situation, there will be pole splitting and so on. So, and then we can calculate what the closed loop poles will be and whether the circuit is stable or not. And a simple feedback circuit like this is almost guaranteed to be stable. You do not have to work too hard to make it stable or to eliminate ringing and things like that. Okay. Now, we have discussed the other circuit quite extensively, that is when we have a fully differential circuit, and let me show it right here. We could make a common mode detector with buffers, so that the fully differential op amp is not loaded. And you use a transconductor to complete the feedback. Okay. Previously, I had used an op amp symbol here, but it is really a transconductor. You do not make a full fledged op amp in this case. Okay. It is really a transconductor because it has a high output resistance. Now, in this case, when the common mode feedback loop works properly, the common mode of these two voltages will be set to VOCM. MC11, MC12 and this MC11 prime are identical to each other. Okay. And we have this RCM and RCM here, and we usually also have to have these capacitors CCM to make sure that there is not too much delay in the common mode feedback loop. We also have to have Miller integrating capacitors. In the common mode half circuit, it appears between the gate of M34 and the drain. Okay. So, in the fully differential circuit, it will appear between the gate of M3 and M4 and each of the drains. Okay. Something like this. And finally, the actual load of the op amp will be here, C and C. Okay. So, now the circuit looks very complicated, but it is not. This part of it constitutes the fully differential single stage op amp, and M3 and M4 should act as constant current sources in differential mode. Now, the rest of it is for common mode feedback, and this part is for detecting the common mode, this is for the replica, and this is for feeding it back to the gates of M3 and M4, and these are for stabilizing the common mode, that is to make the loop gain of the common mode feedback loop look like an integrating function. Okay. And there are many parasitic poles here and also zeros. and also in the implementation of this, which is a single stage single ended op amp, there will be parasitic poles and zeros, and they have to be adjusted so that you have sufficient phase margin in the common mode feedback loop gain. Now, the moment you add this CCCM in this fashion, what happens is in the differential mode they will load the op amp, because in the differential mode this point is at ground and CCCM will appear in parallel with C. So, you have increased the load capacitance of the op amp, which will reduce the unity gain frequency, but we need these integrating capacitors or compensation capacitors to make the common mode feedback loop stable. We need to have these capacitors, and that will inevitably add to the load capacitance, we just have to live with it. Okay. Now, if you minimize the delays in other parts of the circuit, you do not need to use large capacitors here, and they can be made as small as you wish. Okay. Making them smaller will reduce the excess load on the op amp. Okay. Now, let us look at a couple of different kinds of common mode detectors. In general, the scheme with every common mode detection and feedback is the same. You detect the common mode and you compare it to some reference value, and then you feed it back. Here we needed a replica because the common mode detector has this voltage drop VGS. Okay. Now, all of these can be merged together. The comparison may not be obviously visible. That was the case with this simple circuit. We are not comparing it with any reference that we provide from outside, but the comparison is happening with the gate source voltage of M3 and M4. Okay. So, the output common mode will set itself to VDD minus the gate source voltage of M3 and M4. Similarly, this part the single stage single ended op amp could be merged with the common mode detection. Okay. Now, let us see an example of that. Now, for this illustration I will use the common mode detector without buffer. Okay. This is because it is just more complicated to draw, but you will get the point even without the buffer. The part that I am going to draw now is the common mode detector itself plus the single stage single ended op amp used for feedback. So, this is the common mode feedback that goes to M3 and M4. Okay. Now, sorry, these are MC0, MC1, MC2, MC3 and MC4. Okay. Now, the current that gets pushed out of this can be calculated. The voltage at the gate of MC1 is VOP plus VOM by 2, okay, and the current here and there will be, let me call this IC0, it will be IC0 by 2 plus or minus GMC1 by 2 times VOP plus VOM by 2 minus VOCM. Okay. So, this is this part of it is the input to the differential pair MC1 MC2, that times GMC1 by 2 is the current in each of these transistors, and the total current output, the bias component will be removed and this will be doubled. Okay. So, this will be nothing but GMC1 VO1 plus VOP plus VOM by 2 minus VOCM. Okay. That is the current that tends to flow here if there is a load. Remember, this is going to the gate of the transistor. In steady state there will be no current there, but that is the current that tends to flow through the parasitic capacitance that is at that particular node. Okay. Now, any other circuit arrangement that gives us the same current will work equally well between VOP and VOM, and the output current we need to have the same transfer function. Okay. Now, how else can we do this? First of all, we see that here we have GMC1 times VOP plus VOM by 2 minus VOCM, and this can be rewritten as GMC1 by 2 VOP minus VOCM by 2 plus GMC1 by 2 VOM minus VOCM. Okay, the divided by 2 is not here. It is GMC1 by 2 VOP minus VOCM plus GMC1 by 2 VOM minus VOCM. Okay. So, now each of these is a certain difference voltage. This is between VOP and VOCM, and that is between VOM and VOCM. And we know that we can generate currents which are of this form by passing this differential voltage to a differential pair. Okay. So, what I will do is I will have two differential pairs. VOP and VOCM, VOM and VOCM. And I add up the currents. Okay. Let us say I have IC 0 by 2 flowing here, IC 0 by 2 flowing there, and then these transistors let us say each of these transistors is half the size of the MC1 used in the previous circuit. Okay. So, we have half the current of before and half the device size as before. When I say half of MC1, half the width. Okay. So, the GM of these transistors is GMC1 by 2. Okay. So, what happens is in each of these there will be a differential current. Now, these two currents will be I naught by 4 plus minus GMC1 by 4 VOP minus VOCM, and in these two transistors it will be I naught by 4 plus minus GMC1 by 4 VOP minus VOCM. Okay. And we mirror this current as usual to remove the bias component, and if you calculate the total current that tends to flow out of this, if there is a load capacitance or a voltage source, will be the bias current sources will cancel out, and we will have GMC1 by 2 VOP minus VOCM plus VOM minus VOCM. Okay. This is exactly the current that we had earlier. We had this plus that one, which gives you the same expression as this. Now, this is a circuit in which the common mode detection and the transconductor are merged together. What we have done is we have taken the single stage single ended op amp and split up the input transistor pair into two parts, and also made the tail current half. Basically, the differential pair is split into two halves. So, each half has half the GM as before. Okay. To one of the differential pairs we apply VOP and VOCM, to the other one we apply VOM and VOCM, and finally, when you add up all the currents together, what you will get will be GMC1 by 2 VOP plus VOM minus GMC times VOCM. Okay. This is exactly the quantity that we wanted. So, this circuit also can also be used for common mode feedback circuitry. And how do we use that? Let me copy this over. So, I will remove all of this stuff. This is one of the differential pairs, and this is the other differential pair. Add up the two currents together and mirror it to the other side. I also add up these two currents. Okay. And this is the output of the single ended op amp, which is used for common mode feedback. Okay. So, we complete the feedback loop in this way. The rest of the circuit remains the same. The CCCM is the integrating capacitor, if you want to think of it that way. Alternatively, you can think of it as providing feedback around M3 and M4 for high frequencies. Okay. For low frequencies, the feedback goes through this complicated circuitry, which has a high DC gain. For high frequencies, the feedback around M3 and M4 is closed through CCCM. Okay. This is VOP and that is VOM. So, this also works equally well, and again because we have connected gates of MOSFETs to the differential pair, there is no resistive loading of the differential pair and the DC gain is not compromised. Okay. So, you can think of a lot of circuits like this. I will quickly discuss one minor variant, which is actually more frequently used. Now, if you look at it, imagine the quiescent condition where both VOP and VOM are equal to VOCM, then this voltage and that voltage will be the same. Okay. So, you can simply connect those two together. In that case, you see that this transistor and that transistor are in parallel. The gate is at VOCM, the source is the same and the drains are also connected together. So, I will redraw this differently. I will show these two transistors like this, okay, and they are added together, and this transistor, which is of twice the width. So, if this is WC1 and WC1, this will be 2 WC1, okay, and the total current is IC 0. Okay. So, this circuit is the same when the op amp is in quiescent condition, when VOP and VOM are equal to VOCM. Now, it turns out that this circuit has some advantages when VOP and VOM are different from VOCM, how the circuit behaves and so on. It is somewhat advantageous to have this circuit with the two sources tied together than the previous one. So, this circuit is also used quite often, okay, and it has the same benefits of not loading the differential op amp. Okay, it does not load the op amp in the differential picture. So, this also is some circuit which has a merged in which the common mode detection and the transconductance are merged together. Okay. Now, there is a huge variety of common mode feedback circuits and you can think up your own circuits as well. So, I will not go into the details of all of that. We have looked at a couple of them and we will use it for the two stage op amp as well. There is one more common mode feedback circuit that we will discuss, but in general the principle is the following, that you have two current sources, one on top, one on the bottom, and you have to adjust one of them. So, you need a variable current source, and one easy way of doing that is to have a MOS transistor and vary its gate voltage. That is what we have been doing so far. Now, there are many other variants as well. you can have a degenerated current source and vary the degeneration resistance. That gives you yet another type of common mode feedback circuit. And similarly, the common mode detection and the way you amplify the difference between the detected common mode and the reference voltage can be very different. So, by combining all of these, you can easily come up with many common mode feedback circuits. Okay. Now, exactly which one you use depends on the details, like the signal range over which these circuits operate, how stable they are, how fast they are, and so on. Okay. So, we have discussed the single stage fully differential op amp quite extensively. Now, the differential picture is extremely simple. In fact, it is simpler than the single ended single stage op amp, because the mirror pole and 0 go away, and this behaves like a truly single pole system, okay, with the pole very close to the origin. That is, it behaves more or less like an integrator, and all the other differential characteristics also we have calculated. Now, what we will do is to go on to the two stage op amp, which we said was an improvement over the single stage op amp. I am not going to discuss the cascode op amps in detail. The cascode op amps are nothing but the single stage op amp with each transistor replaced by a cascaded transistor. Okay. So, the common mode feedback works exactly in the same way for a cascode amplifier as it does for the simple differential pair op amp. Okay. And all the arguments that we made so far apply also to the cascode amplifiers. So, I will not discuss it further. You can make either the telescopic cascode or the folded cascode fully differential very easily. Okay. All you have to do is to add a common mode feedback circuit in the manner that we just described, and as with the simple single stage op amp, if you have resistive loading because of the common mode detection circuitry, that will compromise the DC gain. You are constrained to use common mode detectors which present a high impedance, that is basically the gate of a MOS transistor. Okay. So, besides that, there is nothing special about common mode feedback circuits for telescopic and folded cascode amplifiers. I am assuming that you will be able to work it out yourself. Now, we will go on to fully differential two stage op amp. Okay. Now, let me first draw the single ended two stage op amp. This is the first stage with a differential input. And the second stage is a common source amplifier. Okay, and we can connect some load to this point. Now, when we make it fully differential, the output also must be differential. So, first of all, the first stage will not be a differential to single ended converting stage like this, it will also be fully differential, that is the inputs and outputs are fully differential. Okay. And to make the second stage differential, we need to add a counterpart to M11, let me call it M13, and this is M14. Okay. And the bias for this has to be properly adjusted, so that the currents from these two equal the current in this. Similarly, the bias for M12 and M14 has to be properly adjusted, so that the currents in M12 and M14 exactly equal the currents in M11 and M13, and this is done using common mode feedback. So, what I have here is a fully differential two stage op amp, but showing only the differential signal path components. Okay. I have not added the common mode feedback circuitry. Now, we need common mode feedback to the first stage and the second stage, right. In both stages, the current from the top and the current from the bottom has to be exactly equal to each other. Okay. So, we will see how to do the common mode feedback for this particular op amp. There are now many more options. Okay. One possibility is we start with remember the first stage here, this is a single stage fully differential op amp, right, this part of it. So, we can start with making the single stage fully differential op amp with common mode feedback, that is I will show this as a box here. This box includes common mode detection and feedback, and the feedback as you know finally comes to the gates of M3 and M4. Okay. Now, we will look at the details of this, but the common mode feedback circuits that we have discussed so far will work perfectly well. So, now the output common mode of the first stage is stabilized. Okay. Now, only thing to figure out is what the output common mode is stabilized to, that is the value of VOCM. Now, before let us say we had this particular circuit, in this case the output common mode voltage will be equal to VOCM. Okay. What should be the value of VOCM? We did not discuss that, but it is kind of straightforward. There will be certain output swing limit for the fully differential op amp. Okay. Now, VOCM should be in the middle of that range, so that you can swing the maximum possible. Okay. I did not discuss the swing limits of the fully differential single stage op amp, but again it is quite simple. I will not show any of the other details. This is how it will be operating, okay, and the outputs are here. We know that if VOP becomes very large, M4 goes into saturation, or M3 if VOM becomes very large. Similarly, if VOP becomes very small, either M1 or M2 go into triode region, that is if VOP becomes small, M2 goes into triode region, if VOM becomes small, M1 goes into triode region. Okay. And the limits are straightforward. The limit on VOP is VDD minus VD sat 3 for a current of I naught by 2 on the upper side, and on the lower side it is V bias plus Vt of M1 and M2. Okay. I am assuming that the signal swing Vd is so small, so it does not affect the limit. Okay. So, this is the case. Now, in quiescent condition VOP and VOM will be equal to VOCM, okay, and we should set VOCM to be in the middle of this range. So, that this is VOCM and you have the maximum possible room for VOP and VOM, okay. That is the idea. So, that is how you select VOCM. Now, we have the fully differential two stage op amp, and we have assumed that the first stage has a common mode feedback circuit, that is the first stage is a fully differential single stage op amp with its own common mode feedback circuit. Now, what should be the quiescent output voltage of the first stage? We need a certain bias current, let us say I12 in the second stage. Okay. The common mode voltage at the output of the first stage is equal to VOCM, and VOCM produces a certain current in M11 and M13 in the quiescent condition, and that should be equal to the desired bias current in the second stage. Okay. Now, I hope that this part is clear. In the single ended two stage op amp, what happens is we have a differential pair with current mirror, and that drives this transistor M11, and M12 is a fixed current source. When you put the op amp in feedback, the current in M11 becomes equal to the fixed current source supplied from the bottom. When you have a fully differential two stage op amp, the situation is different. Okay. Now, in this case the first stage is a fully differential single stage op amp, and its output produces certain current in M11 and M13, and we should, using another common mode feedback circuit, make sure that M12 and M14 carry the same current. Okay. They are not fixed current sources at the bottom in this particular arrangement of the two stage op amp. So, VOCM for the first stage, let me call it VOCM 1. VOCM 1 must be such that the desired quiescent current I 12 flows in M 11. Okay. And how do we produce that VOCM 1? So, let us say we make a replica of M 11. Let us say M 11 has a certain width by certain length. Here we make, let us say, some sub multiple of that width divided by 11, and we bias it with a current I 12 divided by N. Okay. That is, the desired current in M 11 is I 12. Here we put I 12 by N just to save current, and then we also have a transistor whose width is 1 over N times the width of M 11, and then we diode connect it. Okay. This will provide VOCM, because we know that if this VOCM, the voltage here were directly applied to the gate of M 11, the current in this would be exactly equal to I 12, the desired value of I 12. Okay. Now, it is not directly applied to M 11. What is happening is this VOCM goes to the common mode feedback circuit, and the value here and there in quiescent condition when Vd is 0 will be equal to VOCM. Okay. And that will give us the desired current. So, basically this VOCM is not something that we independently set to be some absolute voltage, but we derive it using a transistor level circuit. Okay. Now, this is again another example of a replica. We have to adjust VOCM so that the output stage carries a certain current, and we can't put it to a voltage source and adjust it and hope to give the right current, because changes in transistor threshold voltage and current factor will give you different currents if you bias the gate at a fixed voltage. So, you bias it with a current mirror basically. Okay. So, that is all that is there to it. Now that VOCM 1 is derived like this, let me correct these things. It is VOCM 1. The output has to be again common mode stabilized, the output stage. So, the gate voltage of M 12 and M 14 must be adjusted using another common mode feedback loop. Okay. And what is this now? It calculates the common mode voltage of the output. Let us say this is VOP and VOM. Okay. And it will have some common mode voltage, which will set the output common mode voltage to the desired value. And what is the desired value? Again we look at the signal swing limit of the output stage, and we set the common mode voltage VOCM 2 to be in the middle of that stage. Okay. Now, we will see how to realize this common mode feedback circuit. Now, before we go into the details of the common mode feedback circuit of the two stage op amp, let us quickly go through the differential half circuit of the two stage op amp. Okay. To avoid clutter, I will remove the common mode feedback circuits from this. We know that the common mode feedback circuits do not play a role in the differential picture. They may add a load to the differential picture, but that is about it. Okay. This is the point to which we apply the common mode feedback of the first stage, and here is the common mode feedback of the second stage. Okay. Now, in the differential half circuit, what do we have? We have this point to be ground and that point to be ground, okay, and also this point to be ground. So, we will have M 1 with its source grounded, M 3 with its gate grounded, okay, and this is M13 and M14. Okay. So, this is the output. So, this is the positive input Vd by 2 and this is the output Vop. This is the differential half circuit of the fully differential two stage op amp. This is the first stage and here we have the second stage. Okay. As before, the differential half circuit is extremely simple. We have a common source amplifier M1 followed by common source amplifier M13. Okay. Now, to make a two stage op amp, we need to have the integrating capacitor here that I did not show earlier. So, that is there in the complete circuit, it will appear here and there. Okay. Now, in terms of transconductors, the single ended two stage op amp looks like that. This is GM1 and that is GM2. Okay. Now, the fully differential one looks like that. Okay. So, it is just a fully differential version of the same circuit. So, this circuit is again extremely easy to analyze. Now, because of the symmetry, we do not have the mirror pole and 0 in the first stage. In a single ended two stage op amp, you have that because one half of the current is mirrored. In this case, you do not have that. So, the transfer function of this is lot cleaner than the single ended two stage op amp. Now, I will not work out this thing, but you already know we have analyzed extensively the frequency response of a common source amplifier M13 with a capacitor C between its drain and gate. Okay. So, the DC gain of this will be the gain of the first stage GM1 by GDS1 plus GDS3 times, that is very easy to see in the half circuit, we have GM1 loaded by GDS1 and GDS3 times GM13 divided by GDS13 and GDS14. I am assuming that there could be some load here which will be GL, and the unity gain frequency of course will be GM1 by C. The non-dominant pole will be at GM13 C by C plus C1, where C1 is the parasitic capacitance here, that is the conductance due to M13 being in feedback. Okay. I will neglect the other terms associated with that, and then you have C and C1 in series plus any load capacitance that is connected. Okay. So, we have a load conductance GL and a load capacitance CL. So, this is what we assume. Okay. In addition to this, we will have an RHP right half plane 0, which is at GM13 by C, and this can be cancelled using RZ. Okay. That is using a resistance in series with the integrating capacitance. So, the two stage fully differential op amp is just a fully differential version, that is all we do. The first stage is already almost differential, it uses a differential pair, but we do not use the current mirror load, we use the current source load, and the second stage we have to replicate it to the other side and we get the fully differential op amp. The gain and frequency response are very similar to that of the single ended case. Okay. So, in the next lecture we will look at how to do the common mode feedback stabilization for the fully differential two stage op amp. Thank you.